So this is probably the last time you'll see this word in all of physics, right? Like that's kind of a crazy thing, but we have to acknowledge it exists. What is the temperature for freezing water on the Fahrenheit scale? 32 degrees for whatever reason. Right? Okay. Celsius may make a little more sense.
0.
Okay. Whoa, hi. And Kelvin, what's the Kelvin temperature of ice or water freezing to ice?
277 degrees.
Just take degrees.
He did, and he got a look. Because why, Logan? Why did you get a look?
Because there is no degrees.
Right. Yes. Degrees Fahrenheit, degrees Celsius, Kelvin. Okay? Makes me cringe whenever anybody says it. It's not right. There are no degrees Kelvin. Got it? Got it. Okay. So we don't really care about the conversion to Fahrenheit. Like you can do it. You can look it up. There's a 5/9 or something in there, whatever. The thing that you really want to know, though, is that a temperature in Celsius and a temperature in in Kelvin are directly related, right? It's a nice little cute thing. How do you get from Celsius to Kelvin? Subtract 273? I'm sorry. Did I say it backwards? I apologize. Is that a true statement?
Yeah.
Okay, that's what we want to know. So it's just that magic 273. What's up with that? Why is that true? It kind of comes over to here. Question number 2 said, why are there no negative numbers on the Kelvin scale? Yeah, and that's a really important thing to know, right? Is that, oops, that didn't work very well for me. Let's try that again. There we go. So 0 Kelvin is what we call absolute zero. So that sounds important, right? Absolute, like what? What does that mean? How about you raise your hand so we can have one conversation, like, as opposed to a big muddle of grossness.
All matter stops moving.
All matter stops moving. So, you have something and it's wiggling, right? And that wiggling is due to energy, right? Okay? The temperature of something is really measuring the kinetic energy of the molecules. Does that make sense? Okay? So as you cool them down, what happens to that kinetic energy? It goes down. And there's a point at which the wiggling stops. That stopping point is absolute zero. You can't have negative wiggling, right? You can't have, like, that doesn't make any sense. So absolute zero is as cold as anything can be. Bless you. Gabe?
I have a question.
Yeah, what's up?
Can it stop moving? But what about uncertainty?
Right, so there are limits to it, and here's the other, well, hold on, can you hold on to that for just a second?
Okay.
Because it's going to fit into here in just a sec. Is that okay? Okay, so hold on to that for just a second. So I want to write down absolute zero, I want to remember this, and I want to also write down, just so you know, so you can use this as part of your notes, or you can write notes about this, but I want to make sure that this is something you know, okay? So the temperature is really a measure, or is related to, it's a measure of the average internal energy in a material or a system or a whatever, in a body. Okay? When the molecules have no kinetic energy, we then say that it's at absolute zero. How in the world did we come up with that idea? Does anybody know the history of that, like where it came from? It's kind of cute.
Some European scientist.
Blanket statement for pretty much everything in, yeah, no, that we're not going to just take that. I'm sure, I don't know who it was. I just know what they did. So this is just this is for, This is not something that I'm going to test you over. It's just kind of interesting. If you take a constant volume gas thermometer, so there are lots of different kinds of thermometers, right? The thermometers that we're most used to seeing are either digital thermometers, where the resistance varies with temperature. Okay, that's all electronics, blah, blah, whatever. And there are also those, like alcohol thermometers or mercury thermometers, right? What happens in a mercury thermometer or an alcohol thermometer? What happens to measure temperature? What's that?
It heats up or cools down depending on the temperature of what you're measuring.
The stuff, right? So I put the thermometer into the stuff, and the thermometer is going to heat up or cool down. And what happens inside the thermometer that helps us to know the temperature?
The mercury expands or compresses.
Right. Yeah. So there's like a change in volume. Does that make sense? Right. And so it's expanding when it gets warmer, and so then it just it goes up the calibration, and then you know exactly how warm it is. Right. So that's a different kind of thermometer. You can make all of these different kinds of thermometers. There's a really lovely thermometer out there that's called a constant volume gas thermometer. And if so the volume isn't changing, that means you may surmise that as the temperature changes, the pressure is going to change. Okay? That if you've done the reading, then you may have that kind of inclination in your brain. And so what they did with this constant volume gas thermometer is that they took different gases and they measured the temperature and the pressure of the gases, and they found that there was a relationship. Oh, go figure. They found out that there was a relationship, and the relationship looked something like this. Like maybe at this temperature, the pressure was there, and then at this temperature, the pressure was there. And you can take that. I mean, you don't want to just take 2 data points, right? You want to take a bunch of data points, but they were all on a nice little line. That's kind of cool. And so we can connect all those dots into a nice little line like so. And then we have a different, and this, oh, by the way, is measured in degrees Celsius, because we didn't really have this concept of Kelvin yet, right? And then there's another one over here, and we measured it a few times, and it looks something like this. And then we did it again, like this, and we got something like this. And the physicists, instead of just saying, oh, that's cool, decided to take those lines back. And if you draw those lines back and you do it well, I'm not guaranteeing that this one worked out well, but we'll just kind of see what happens. Whoa, hi. And let's see how well I did this morning. Pretty darn well. What happens to all of those lines? Whoa, they hit the same spot. So when the pressure, what is pressure?
It's the measured force of all the little particles of gas hitting.
Right, so literally pressure is particles of gas that are hitting the walls of the container, right? And so if there's pressure, that means there's movement. And if there's no pressure, that means there's no, okay? So when the pressure goes to 0, all of the temperatures approach the same value. And you could probably predict now then what that value is. I'm thinking it might be negative 273 degrees Celsius, right? That's magic. Whoa! That is where absolute zero comes from. Okay? So it's not like they just were like, it must stop. Like there's a reason for it. Okay? I just think it's kind of a nice thing to know where that actually comes from. Questions? Yeah, go ahead.
If you had like a jar that was at, and the gas inside was at 0 Kelvin, because, for instance, if you have a wine bottle that has really low pressure inside, you can't pull the cork off very easily. Would you be able to open that jar at all that was at 0 Kelvin?
So,
Right.
in a hypothetical situation, because this is all hypothetical,
Yeah.
I would say probably it would, no. I mean, like, I think that you can extrapolate down from where you were going, right? As the pressure goes, I think the answer would be that it would be exceedingly difficult, if not impossible. But let's talk about getting something down to absolute zero first.
Yeah.
Is it possible?
No, not yet.
What's that?
Not yet.
Not yet. Let's talk about that in terms of this last question. This last question said, except that I kind of broke it up into pieces here. What is meant by the statement, a thermometer measures its own temperature? What does that mean? A thermometer measures its own temperature. Go.
It means like when you put the thermometer in a substance, the temperatures equalize. So
Yeah.
It doesn't matter which it measures its own temperature, it is the same temperature.
Right. So just like you did when you were doing your lab, right? And you were measuring the temperature, actually while it was going up, really what was happening was that the thermometer was changing temperatures, right? To reach, what's that word, that phrase? Thermal equilibrium with the substance or the body, right? Okay, so basically what's happening is that the thermometer, bless you, reaches thermal equilibrium with the body. And that's the point at which you can actually measure accurately what the temperature is. So you are changing the temperature of the body a little bit in doing that, right? Does that make sense? Okay. Probably not a lot because we're trying to avoid, we make this thing small enough that it's going to change temperature much more than the body is. Okay. So I take something and I cool it down, right? And I'm measuring the temperature of it. And the thing that I'm measuring, the thing that I'm using to measure the temperature, has to be, like, there has to be some sort of reading that I can see. So it has to be out in my space. So I've got a beaker of, I don't know, we'll start with water, right? We'll cool it down. Okay? We'll watch the temperature plummet. But that means that the temperature of the thermometer is also doing what? Going down. Okay? And so we can watch it go. But are we ever going to get to a point where the thermometer is going to say 0, actually? No. So let's say instead I want to take, okay, so I'm not going to put the thermometer in there. I'm just going to take my beaker of, insert whatever here, right? And I'm going to cool it down. I'm going to make it really cold. Really cold. Right? Like really close to 0. And then I want to know what the temperature is. So I stick my thermometer in. What happens to the temperature of that body then? Goes up. Does that make sense? So we can get things really cold. Like, I don't know. One of you probably knows much better than I do. What's that?
We've gone down to nanokelvin.
There you go. Nano. So that's 10 to the negative 9th. So we're really, we're close. But have we actually made it to 0? No. Will we ever? Probably not. Like, it's kind of hard to do that. So, I'm not saying, you can never say never, right? But it's like, it's not a super possible, easy thing to do. We can get close. What's that?
Say if you had a particle that moved backwards in time, then you get some negative color.
I disagree. Kinetic energy, wait, no. No.
Open your mind.
You can't have negative kinetic energy. 1/2 mv squared, there's no negative in there to get negative. Right, you get, no.
Well, you can try it.
Wrong. Sorry. Because then it's not right.
That's the easiest way to do it.
You could have like a 5th dimensional pickle jar in a universe.
Yes, with that 5th dimensional pickle jar, everything is possible.
Yeah.
Yeah. Okay, so the principle of thermal equilibrium is one that's really pretty obvious. And just like there are Newton's laws of motion, right? You got the first law, second law, third law, blah, blah. There are also laws of thermodynamics. Okay? If you've read the article, you know that the second law of thermodynamics is like the big one. It's so important. The first law is pretty darn important as well. The funny thing is, historically, right, it wasn't like there was just one person that sat down and wrote all these laws like it was for Newton. Okay? They had established this first law and this second law kind of in the way that happened. And they're like, oh, but wait, there's actually a law that's more fundamental than that. So we need to name it. We're gonna name it, and this is, I'm not making this up. This is like actually for real true. It's the 0th law of thermodynamics. And it's something that's kind of important to know. It's pretty obvious and probably I'll be like, yeah, well, duh. But it is important to articulate. So let me make sure that I do it for you so that you know it, so that you can be well versed in it as well. If two objects are in thermal equilibrium with a third object, then what do you know about those two objects?
They have the same temperature.
Yeah, so they're in
Equilibrium as well.
thermal equilibrium with each other. Yeah. Not a huge surprise, right? But it is important, so I just want to make sure that you know it. This is the principle that makes thermometers work. Okay, that's why they work. Okay. Issues, questions so far? We good? Yeah. One other really important definition. So there are actually two in here, but I snuck one in before I told you it was coming. So temperature, that would be something that I want to make sure that you have written down. Temperature is a measure of the average internal energy of a body. So that's an important thing to know. There's another word that a lot of people, if you ask somebody on the street randomly, they'll be like, oh, they're the same thing. But I'm here to tell you, that's wrong. They are not the same thing. Temperature is one of them. The other word is heat. We've talked a little bit about heat, but we haven't really articulated it explicitly, so I want to make sure that we do that. What is heat?
Transfer energy.
Yeah. So it's a transfer of energy, or it's a flow of energy and I'm going to say thermal energy, okay, between bodies. Okay. An object has energy, or I'm going to say has internal energy, okay? An object does not have heat. You can't have heat. It's not a thing like that. Okay. One way to think about it is that heat is a flow or a transfer of thermal energy, just like work is a transfer of mechanical energy. Does that make sense? You don't have work, but you do work, and we have heat flow. Okay, so that it's a just a piece of information that I really want to make sure makes sense. So far, so good. All right, we'll keep going. Whee! A couple of quick definitions here. I think you know them, but let's just make sense or make sure, because I would be sad if I skipped them. The mole. You've discussed the mole before, right? Seems like in chemistry they spend a lot of time on it because it's a very stressful thing. It doesn't need to be a stressful thing, my friends. You can go order a mole of donuts just like you can order a dozen donuts. It's just going to be a whole lot more donuts. Okay? That's all it is. What is a mole? Where did it come from? Why do we have it?
Is it like the volume of a cubic foot? I don't know. That's not right.
No, that's not how it's defined. I mean, It'd be a cubic foot of something, I'm sure, yes, but I don't know what. Yeah.
Isn't it how many particles of a certain element make up one atomic unit of that element?
There's like 6 point
Mhm.
6.023 times 10 to the 23rd.
Like, I know the number!
But it's like
I know the number! Yeah, yeah, yeah.
Isn't it that many particles make up 1 mole? Like that many phase particles of that substance make up 1 mole.
Mm-hmm. Do you know where it was defined from? What element it's defined from? Carbon. It's defined from carbon. So it's the amount of substance that contains as many particles.
It's a carbon 12 atom, though, isn't it?
Yes, yes. As 12 grams of carbon 12. Okay. 1 mole has a value of 6.02 times 10 to the 23rd. What? 10 to the 23rd anythings. Objects. Okay? I can have a mole of frogs. I can have a mole of a gas. I can have a mole of people, right? Like, maybe not, that's a lot of people, but you get the idea, right? Like, it's just a counting number. That's all it is. It is the SI unit for amount. So the SI unit for length is a meter. The SI unit for amount is a mole. It's just a really big base unit. So that it is what it is. Is that okay? Okay. We can define it a little bit more carefully if we're talking about an atom or some sort of sample. N, little n is the letter that we use for the number of moles in a sample. This should be good review stuff for you here. Big N is the number of particles. And then we're just going to divide that by N sub A, which is the number of particles per mole, also known as, what was his name? Avogadro, yeah.
Wait, the mole is denoted N sub A, like Avogadro.
Yeah, so N sub A is Avogadro. It is 6 pointers 10 to the negative, or 10 to the negative, excuse me, 10 to the 23rd. Yeah, I mean, that's the notation that I've seen. That's what we use. Yeah, yeah.
How would they measure that? Like, if that many particles? I mean,
You get out a little, like, you count? I don't know. Like, what do you, I don't know what you're asking
how would
exactly.
they measure that?
You can go to the little gate.
Grad students? I guess, I mean, like,
How would they get that?
we,
Like, that number, like exact, like precise number.
well, I mean, who knows how precise it is because there are 23 zeros after that, right? So, yeah, I mean, it's approximate. Just don't tell the chemists that because they might get mad. I don't know the history of the mole, to be honest. I think that's what you're asking. Is like, where did the number actually come from? Is that what you're asking? And I don't honestly know. I'm sure that somebody on Google could tell you. And I would actually be very interested to find out. I just don't have the answer for you right now. You could look it up, though, and let us know. Will you report on it for us? Would take you like 5 minutes. Okay, there you go. All right, something to look forward to on Thursday. Make sure you come back. All right. So now that we know what a mole is and we know all of that stuff, we can broaden our horizons a little bit. We can have a little conversation about something we like to call the ideal gas law. Yeah! Are you excited?
Yeah.
I think you've all learned the ideal gas law, yes? Maybe in chemistry in 9th grade? Did you guys do this in 9th grade chemistry? Because you remember it so well, right? It was ingrained in your brain. Let me tell you about the ideal gas law. So the ideal gas law is a law about Ideal gases. Okay, thanks, Miss Carmeline. That's really great. What's an ideal gas?
It's a gas.
What's an ideal spring? Let me back up. What's an ideal spring?
One that has no friction.
Right, right. It's like this happy little thing that's not going to lose any energy, right? It's like the perfect systems, perfect scenario. Ideal gas, kind of the same thing, right? So we're talking about monatomic gases. We're talking about gases that are not, there are no bonds between the atoms. They're just kind of bouncing around. So it's really all about like little, you can imagine these gases as just little billiard balls that are bouncing around in a box, okay, or in a container. Okay, that's the thing you really need to know. So we use it as a model for real gases. Okay. At low density, so that the molecules themselves don't really interact with one another. Okay? And the ideal gas law is something that we call an equation of state. And that's an important thing. There are many equations of state. This is the one that we cover, that we articulate in this way. And it's just kind of a phrase that you'll see, so I want to make sure you're aware of it. The phrase equation of state means that it talks about the physical conditions of a system and only talks about equilibrium states. So we're not talking about things where there's a transition. So there's no calculus here. Okay? So it's just at this situation, or at this situation, or at this situation. We're not talking about transitions. Okay? So it involves, I'm going to just write that down, the physical conditions of the system. So it describes the conditions, and it only applies, we'll say, at equilibrium states. We will talk about transitions soon, okay? Not in a super calculus-y way, but just in a kind of being aware of the changing way, just not yet. The ideal gas law relates 4 different conditions. The 4 conditions are pressure. Pressure is marked with the letter capital P, not to be confused with small p, with a vector hat over it that's momentum, right? Like we don't want to go there, okay? And what is pressure? We talked about that a little bit before, but we can write it down. Force per area. So just so we don't forget that, I'm just going to write that down. Okay. It relates temperature. Okay. The temperature is marked with a capital T. And the temperature must be measured in Kelvin. If you remember when we were talking about the other, when we were talking about the calorimetry stuff on the first day, we said it could be Kelvin or it could be in degrees Celsius, because we were talking about a change in temperature, right? And the change in is going to be the same for Kelvin and Celsius. In this case, because we're actually talking about the physical conditions, that has to be in Kelvin, or else this relationship doesn't hold. Okay? We are talking about the number of moles. So we'll say the amount of the gas, marked with a little n. And then we've also got the volume, which is marked with a V, capital V. Yeah. So the way that this works is that you can relate all 4 of these values, and if you keep 3 of them, or keep 2 of them constant, change one, the other one's going to change, and we want to know how. Okay? So in chemistry, I believe, and I don't know what you guys do in AP chemistry, but I know that in a lot of like just regular chemistry, texts and things. They're like, and if you change this one or this one, then you have Charles' law. And if you have this one, it's Boyle's law. And da, da, da. And there are all these different laws. And the game is that they're just like subsets of the ideal gas law. So like we don't need to memorize them. But we're going to look at them kind of piece by piece. If you have, so case 1, let's say that we have a constant volume gas thermometer. Oh, we talked about that earlier, right? Thermometer. In the case of a constant volume gas thermometer, what do you think is going to stay the same?
By the volume.
You're going to go with the volume, right? And if it's a thermometer, like if it's some sort of container, what else do you think might stay the same? The amount, right? So delta V is going to be 0 and delta N is going to be 0. Okay? What's going to happen to the temperature as the pressure changes? Are they going to change? Yeah? I kind of alluded to it a little bit earlier. Is it going to be a direct relationship or an indirect relationship? Direct, right? As the temperature goes up, the pressure is going to go up. So we've got a direct relationship there. That's somebody's law. I don't remember who. I don't keep track of these things. Is that Charles? There you go. Somebody's got to know these things. It's good that we keep you around. Yay. All right, another situation. Let's say that we're pumping up a tire. Okay? If you're adding air to a tire, what are you definitely changing? The amount, right? So we know that N is changing. And in doing so, what else are you changing? The pressure. What things are staying the same, pretty much? The temperature. So delta T is going to be 0. And what else? The volume. Delta V is going to be 0. As the number of moles or the amount of the gas goes up, what's going to happen to the pressure? Does that make sense? Okay? It's not like you would add air to your tire and it gets like that doesn't make any sense. Right? What? That doesn't make any sense at all. So that's going to be a direct relationship as well. Another situation. Let's just keep going. Number 3. This one I don't really have a lovely name for, but let's just imagine taking a balloon and squeezing it. There are 2 E's in squeeze. Thanks. I like that attitude. Sure. Why not? Squeezing a balloon. So, you have a balloon, and you squeeze it. What things are staying the same? The amount, I hope, unless it pops, right? So delta N is going to be 0. The temperature is going to be 0. Or change of temperature is going to be 0. Not the temperature itself. That would not be possible. Right?
Unless you're traveling back in time.
Right. Well, yeah. In the 5th dimension with the pickle jar.
Yeah.
In which case, of course, it would work. Yeah. As you squeeze that balloon, what are you doing to the volume? What's it doing? Going down? And what's happening to the pressure? Oh, well, that's exciting. There's something different, right? Yeah. So that means that instead of saying that V is proportional to P, we're going to say that there's got to be an inverse in there somewhere, right? So like V is proportional to 1 over P or something like that. Okay. This needs to be absolute pressure, by the way. You can read about that. We're not going to get into that a lot, but there's a little bit in there. So that's going to go down, or it's going to be a nice little hyperbola. That's Boyle's law, I think. Yeah. Go Boyle. We're going to talk about Boyle's law on Thursday. Yay, that'll be exciting. Do a little lab so that we can count it as a lab, and that'll be a good thing for all of us. Okay? We can put these things together. I just want to get them put together because we can. So temperature is proportional to P. Amount is proportional to P. V is proportional to 1 over P. We can put those 3 things together, those 3 ideas. Okay? And we can say then that P is proportional to, well, temperature and N and over V. We like things that are equal as opposed to proportional, right? We like to be able to set something. So we need to have a what?
Constant.
We need a constant in there, some sort of constant of proportionality. Okay, let's get one. Let's call it the universal, because that's fun, right? Gas constant.
How exactly did you make the P's proportional? You just combine all of them, I guess.
Well, yeah, so I'm just saying P is proportional to T.
Uh-huh.
So that's this.
Mm-hmm. Oh, okay, then
Yep.
you flip to one of them. Yeah.
Does that make sense?
Yeah.
Yeah, yeah. Yeah. Universal gas constant is marked with the letter R. Universal, I don't know. I don't know why they chose R. Probably for some good reason that I am not particularly aware of. It has a value of 8.31 somethings. 8.31 somethings. I'm trying to figure out if you can figure it out from here.
We never said what units we were doing anything in.
That's true, we didn't. So let me tell you what units we're doing things in. Mostly because I want to get through some more stuff here. So they found this all experimentally. Kind of like they found the universal gravitational constant experimentally. Same kind of deal. Except it was easier to do. Joules per mole Kelvin. Okay. And because people are, for some reason, really afraid of things being in denominators, right? We've been through this, right? Like, oh no, not a denominator. Generally, when we write the ideal gas law, we'll write it as PV is equal to nRT. Sometimes people like to articulate this as a word, and I don't want to hear it. So if you want to say it in your head, that's fine, but it's not a word. The equation for the ideal gas law is PV equals nRT. I'm just going to leave it right there. Is that okay? I don't know. It's gross. Okay. What's that? Did you have something to add, Nathan? Are you okay?
Good.
Okay.
I just said nerd.
Right, and that's what I... Gross, don't do it. Okay. Sometimes we don't like to deal with things in terms of number of moles. We like to deal with them in terms of number of particles. And if we do that, we get ourselves a new constant. And so I just want to share this information with you too, so that in case you see it, we can come up with another constant that's called Boltzmann's constant. Boltzmann's constant is marked with a little k and is defined as the universal gas constant divided by Avogadro's number. So then you're really converting this thing into number of moles. Does that make, or number of particles? Okay. Did somebody say why?
I said, whoa.
Oh, okay. Okay. I mean, it's yeah. It's I guess yes. It's awesome, right? In which case, so the value of that is going to be what's like 1.83 times 10 to the negative 23 joules per Kelvin.
And when did you say raise that? Are we done?
It doesn't matter. It just depends. It's one of those things like if you have givens that are in moles, then I would use this one. If you have givens that are in just regular amounts, then you can use this.
Okay.
I think if I'm trying to remember, people have told me this, but I haven't taught this for a while, so I don't remember. I think physicists usually use this and chemists usually use this, but I could be wrong. Is that true, chemists? Can you talk to me? Can you give me any feedback, or do you remember? You don't know. Nobody's gonna
I thought we just used
commit.
moles.
Did you use this one? I don't know. I haven't done chemistry for a long time, and I don't remember what they use, especially. But I mean, it's just a simple conversion, right? It's not like a yeah. If you use K, then the ideal gas law turns into PV equals big N little k T. Okay. that all right with everybody? Jack, you look happy? Happy? Okay. All right. I'm so excited about what's coming next, but I'm trying to decide. So the notes that I'm using are from my AP Physics B days, so they're a little on the calculating side heavy, not as much on the ratio-y side for those of you that are my AP Physics 1 alums. I've got a couple of problems that we could do if you would like. Would that be a helpful thing? Get your fingers moving, get your brains moving a little bit? Okay. So you may want a calculator out. And I'm also going to get you some equation sheets so you can take a look at what they look like. So grab a calculator if you need one. I'll throw a problem up here for you to do. And I do need to define one other thing for you because I forgot to do it already. But I will get there in just a sec once you guys are ready to go. So look at all of these highly prepared students that brought the calculator. And Donald. Where were you off then? You just wanted to stretch? Okay. I'm handing out your equation sheet and constant sheets for this year. Thanks, Lindy, for copying them for us.
Thanks, Wendy.
You will have a copy of this for all of your tests, of course. But this would be a good thing to hold on to.
A little early to be eating pretzel sticks.
You study topic equations.
You guys done the math and electrons? No, it's not but 11 times 10 to the negative 31st.
There you go. You're so welcome.
Whatever.
I'm going to squeeze right between you guys, if I may.
All our old friends are on here.
I know, right?
Gang's back.
They're all back, but it's two-sided now.
I know.
Because there's even more, right? So I think that they just gave you everything that you did last year and everything you're doing this year.
All right.
I think they're just trying to like make sure you're,
It's like 3-party
you know, feeling good about yourself.
variables.
So one little piece, Gabe said this out loud, and I was like, oh yeah, you're right, we didn't. We didn't really define the units that we're talking about all these things in, and I apologize for that. In particular, we didn't talk about pressure and the units that pressure can be measured in. Okay? Just like so many other things, there are lots of different ways that you can measure the units for pressure. One of the common ones is in atmospheres. Where do you think that comes from? What does that mean?
Pressure of the atmosphere at some sea level.
At sea level, right? So the way where the idea comes from, if you think about it, when you're standing on the earth, gravity's pulling you down, right? We know that. But you're also feeling a force from a column of air that's above you. It's kind of weird, like right above you, it's like pushing down on you. Right? Okay? That's atmospheric pressure. That column of air is pushing down on you, and if you stand at sea level, when we're at, you know, I mean like approximately, right? Because like the pressure changes, that's what they talk about, like barometric pressure, blah, 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 right? But an atmosphere is kind of on average the amount of pressure that you would feel if you're standing at sea level. If you go up higher, right? If you go to Mount Denali, yeah, you guys all heard that little scandal yesterday, right? Oh no! Right, you go up to the top of the mountain, they changed Mount McKinley's name back to Denali because, yeah, go read the news, come on, friends. All right, so anyway, you go and stand on the top of a mountain, is the pressure going to be as great? No, because the column of air is much smaller, right? I mean, that's what we're talking about, okay? So an atmosphere is marked ATM. But that's not the SI unit for pressure. We just use it a lot. You'll see it a lot. Does anybody know what the unit for pressure is for SI?
Pascal.
Pascals, yeah. And a Pascal is literally
1
a Newton per meter squared. Yep. Okay, and Pascal is abbreviated PA, and 1 Pascal equals 1 Newton per meter squared, which is literally what we talked about before in terms of pressure, right? Force per area. Okay. The conversion, I believe, is it on here? Yep, it's right there at the very bottom. It's really just a 10 to the 5th conversion, so it's on your yellow sheet. The yellow sheet has all of the constants and conversions. It's the very bottom conversion. So 1 atmosphere is 1 times 10 to the 5th pascals. So that's pretty easy to deal with. Okay. It's actually, I mean, there's actually, it's like 1.013 blah, 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 but whatever. It's close. So that's something you need to know. I think everything else on there you can figure out. So I'm going to let you go ahead and do that. That sound good? Go. Woohoo! So I guess I was going to turn into N is equal to PV over RT. Yeah? So maybe let's just check your numbers that you put in. So what was the pressure that you had?
Pressure. Yeah, I had 105.
Okay, so 1 times 10 to the 5th-ish?
Yeah.
Okay. And the temperature?
The temperature at 290 degrees.
Okay. And the volume?
At 1.35 meters.
Okay. That was,
No.
yeah, so it should be 4/3 pi r cubed. Did you do that?
Yeah.
To find the volume?
There should be 0.0244.
Yeah, my guess is that it was just like a calculator error.
I got it for the 2 dimensions, don't worry.
What?
I put in the area equation, not the volume equation.
So the way you know the difference, right, is that one's squared and one's cubed. And if you look at the units, the squared one's going to be an area and the cubed one's going to be a volume?
Yep.
Yeah, okay, just making sure. Making sure that we're on the same page, because sometimes that's a tough one to do.
For the volume, did you get 0.0244?
Okay. Are we feeling all right? Okay. We'll do some more like ratio-y stuff with this later, but I wanted to spend the remainder of our time today together working on a derivation. In AP Physics C, those of you that were in AP Physics C, we did lots of derivations and it was a good time, right? And I know that they loved it, and I don't want to disappoint. For you AP Physics 1 people, and I'm not trying to like divide, I'm just trying to address everybody's needs and interests. This derivation is not anything that anybody really needs to know, but I think sometimes it's nice as opposed to just like, oh, there's an equation that happens to be on my equation sheet that's got fractions in it and like cubes in it and like why, right? And we've got a little time, so I figured it might be worth giving this a shot. Is that okay? I also like this because it's really nice to see how simple this stuff really can be, okay? So later in the year, we're going to start talking about quantum mechanics. We're going to start talking about like interactions between quarks and like crazy town stuff that makes, I'm going to give you a hint right now, no sense, okay? But all of thermodynamics was established hundreds of years ago. And it works. And it makes predictions that are as accurate as we need them to be. And so we just leave it alone. Like, why mess with something if it's not broken, right? Okay? So the reason that I like doing this is so that you can see that really this whole derivation and all of this stuff comes from like super basic principles. Okay? This is just from physics that we did last year. It's not a big deal. So this kind of topic is called the kinetic theory of gases. And the idea here is that we're acknowledging that if you have a container with a gas in it at some temperature that is not at 0 Kelvin, that those molecules or those atoms or those particles or the whatever are moving around. And because they're moving around, they're causing pressure and da-da-da-da, and we can kind of quantify all of that. But really, we don't have to do it in a very high-tech sort of way, okay? So this is an analysis of matter in terms of, so we're considering atoms that are in continuous random motion. Okay? We're going to model that motion based on just normal, plain old classical physics, okay? So if you hear the term classical, the opposite of classical is quantum, okay? So classical mechanics is everything that you've done so far, okay? Everything that we did last year is classical. Then we get into this quantum crazy weirdness, but we're not there yet, so we're just going to stick with this. As we do this, we're not going to take every single little particle and look at its motion because there are too many of them, okay? So the one thing that we do get to jump into here is this idea of using statistics. So this is what we actually call statistical mechanics. And it's kind of interesting because, you know, in, like, for example, in a physics major or something like that, generally, we need to understand statistics because everything is based on statistics. And we're using the same principles as the statisticians, right? Like the people that are going to become actuaries. But we do it in a different way. We're going to use it in a different application. So just kind of being aware of that. There are people that do statistical mechanics, and that's their thing. So it's just kind of cool to know. All right. So there are 4 basic postulates that we're going to kind of base everything on. Okay? I can't spell today. The first one is that there's a large number of molecules we'll call that number n, each with a mass m, moving in random directions. Okay? With a variety of speeds, just kind of bouncing around in this box. And that's an important thing to know, that when you have a box with a gas in it, and you're talking about the temperature is just you know, talking about the average kinetic energy of these molecules, it's not saying that every single one is moving with the same velocity. But again, on average, statistically, it works, okay? The actual speeds vary really, really widely, okay? But you can look at this really nice distribution of speeds. There was this guy named Maxwell, okay? He's the Maxwell's equations guy. He did like all that E&M stuff. Yeah. Okay. He was the first one to figure this out, and you can actually statistically show this, that the number of molecules plotted on one axis and speed on the other axis gives you this cute little curve that is not symmetrical. Okay? So that this velocity is the most probable, and actually because it's not quite symmetrical, there's a velocity over here that we call the RMS. Does anybody know what RMS stands for? Yeah, there's that one kid in the back that knows. Darn it. I'm going to explain it to y'all in just a minute. Okay? This is the actual average, or they call it the root mean square average speed. Okay? And this is the one, oops, no, go away please, that we really care about. Okay? I think that was on your sheet.
Is that the square root of the square of the velocity of the average kinetic
Yes.
energy of the particles?
Yes. I thought it was on here, but it's not. But we'll talk about what it means in just a second anyway. So the thing to know is that not all averages are created equal. That's the big piece of information that you need to know there. So that's postulate number 1. Does that seem reasonable?
Yeah.
Lots of particles. They all have mass. They're all moving. But they're not all moving at the same speed. Postulate number 2. The molecules on average are far apart from one another. And by that I mean that they're not going to interact a whole lot. They're not like stuck in there so much that they can't move. Okay? These are quicker. Number 3 is that we're assuming that all of the molecules obey laws of classical physics. And it's kind of weird to say that, right? Like, sure they do. Now, you talk to somebody who's really into quantum, they'd be like, well, actually they don't, but here's the thing. Any weird quantum effects are so small that we don't care for this situation. Are you guys with me there? So the stuff that we understand really works, okay? We assume that the only interactions they have with one another are when they collide. So no crazy spooky action at a distance. Okay? And the last thing that we're going to assume, or we're going to postulate, I should say, I suppose, is that all of the collisions with molecules or the walls of the container are perfectly elastic. What's that mean?
They bounce off each other and they don't lose any
Momentum is conserved, and what else is conserved?
energy.
What kind of energy?
Kinetic.
Kinetic energy, yep. So not only is momentum conserved, because momentum is always conserved, but kinetic energy is also conserved. Postulates okay? Okay, here we go. We're going to get through as much of this as we can. I think we can get through it if we move quickly. Draw yourself a little box of gas. There it is. I'm going to make mine a cube because cubes are easy to deal with. So there's my box of gas. Each side has a length L. So each edge has a length L. Each side has an area. We'll call A, which is L squared. Okay. So I fill this up with gas and I seal it off. So I've got a nice cube of some sort of gas. And there is some pressure that we could measure exerted by the gas on the walls of the container, right? How do you know that there's pressure? the literal answer, right? The box doesn't collapse. Absolutely. From an internal perspective, what are those little molecules doing? What? They're what? What are they doing? I think you said it. I just couldn't hear anybody. They're bouncing off the walls, right? They're going. An object in motion, right? It's going to keep going until it encounters some obstacle, like a wall, and then it's going to bounce off. When it bounces off, so it was moving this way. Let's go back to our stuff from last year, this classical mechanics, right? Here it comes. It's got momentum in this direction. It interacts with that wall, and then it's going to go this way, elastic collision. What happens to its momentum? Is it exactly the same?
No.
It's going to change, right? Does that make sense? It's going this way, it's going to go this way, because it's not going to tunnel through. We're not going to quantum stuff, right? So when that molecule interacts with the wall, it applies a force. Okay? If the molecule applies a force to the wall, what do you know about what's the wall doing? How do those forces compare? They're equal in magnitude, right? Yay, Newton's third law. So we know that so when a molecule interacts with the wall, it applies a force to the wall. Let's make sure I write this down well. Which means that the wall also applies a force to the particle. This is like good review stuff for us, right? We can figure out the magnitude of that force because we know the change in momentum. It was going this way, now it's going this way. Change in momentum divided by time is equal to force. That's that impulse momentum theorem. Does that look familiar to you? Have you seen that before? Okay. So I'm going to write this down here as, so this is like m delta v over t. Okay. If the collision is elastic, then we can assume it's coming in with the same magnitude of velocities it's going to bounce off with. So we can say that px, the momentum in, I'm just talking about in the x direction, so here's my molecule. It was going in this direction. It hits the wall, it's going to bounce off that direction. And I'm going to say the magnitude of those two momenta are going to be the same. The direction's just going to be switched. Okay, so if I don't put the vector hats on, then I'm okay. So F is equal to, I'm going to write this as m Vx minus negative m Vx. Tell me if that's okay with you. I want to make sure that I didn't lose anybody there. It's coming in with a velocity, it hits the wall, it's going to bounce back with the same magnitude velocity, just in the opposite direction. So that means that when we have this change in, this one and this one are just going to be in opposite directions. Is that okay? So the force is equal to mvx minus a negative, which is the same as plus, right? I was like, I got that, it's plus, divided by t, which is interesting. That means that we've got a force that's equal to 2m Vx over t. That's one collision, yeah? What's going to happen? Let's assume that this particle is moving directly horizontally. Let's keep it simple for one particle. It's moving directly horizontally. What's it going to do after it hits this wall right over there? Where's it going to go? That way? Until when? Oh, and it's the other wall, right? And it's boink, the boink, the boink, the boink, the boink. It's going to be really fun to watch, right? It's going to be, yeah, my cat would love that. Wah! She'd sit there for hours doing that, right? So after the collision, it's going to bounce back the other way. It goes bouncy, 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 bouncy. Now, we can also talk about this in terms of time. And we can say that the velocity of that particle is equal to distance per time. Is that okay? And if we're talking about, so velocity is like the length per time, but if I want to just know the pressure on one wall, how far does that particle actually travel between two successive collisions on one wall? 2 L's. So I'm actually going to make that a 2L. And I'm going to solve that for T. So I've got 2L over V. That's how long it's going to take between successive collisions. And then one more thing, and then I'll pause here. I've got a T down here, and I've got a T here, and I'm going to put those two T's together. So I can say that the force, the average force from one particle, okay, is going to be equal to 2mvx, I'm going to call it, divided by, okay, well that's going to be 2L over V, that velocity that it has. And simplifying that, I get what? What is it? Okay. I'm going to put kind of like a kind of box around that so we don't forget where we're at. We're going to pause there. We'll start there on Thursday. It'll be